Welcome to this video today. We're going to review the Series RLC relationships and some rules and how to solve them. We're not going to deal with any numbers today. We're strictly talking about the relationships between current and voltage, and then we'll get into our power. So we're going to draw some pretty handy diagrams, hopefully big enough for you to see. But yeah, so we're going to do this. Check out some of my other videos where I actually walk through calculations, made up numbers, things like that through those. And I'll put a link to all of those below, as well as if you're looking for some parallel RLC stuff, I've got a bunch of that as well. So getting started, we're talking about a series RLC circuit. Now, I draw mine in a straight line like this while I'm doing my calculations because I find it much easier to organize my information in columns. But of course, this circuit would actually look something like this in real life, where I have that loop and I really only have one path for current to flow. So that's kind of where I'm coming with this, but I draw it like this just to store my information. Now we know a couple things in series, and one of them is really important. The important thing in series is that I only have, like I said, that one path for current to flow everywhere within that circuit. So Kirchhoff's current law, which tells me current entering a node is the same as a current leaving that node, is really helpful because we have the same current throughout. So now often what will happen in a series RLC circuit is I'll need to calculate that total current. I'll usually know my source voltage. Won't always, but I'll usually know my source voltage, but that's ET, right? I know I'm gonna have a voltage drop again across each one of those loads. So here I'll have, voltage of my resistor. I'll have a voltage drop across my coil, and I'll have a voltage drop across my capacitor. Now, where we would go with this, kind of a couple different ways. I like to look at it like this. I say, okay, well here I have a resistive component. That's an in-phase component. Here I have a coil. A coil has an ohmic value or resistance that's in phase. It also has an inductive reactance, which is out of phase. So we have a little impedance triangle just for that coil. Now with the capacitor, it is all out of phase. So all of my ohms or my XC is completely out of phase, right? So like I said, we have the resistance of the resistor, we have the resistance of the coil, we have the XL of the coil, and we have the XC of the capacitor. Now the cool thing in series, because there is only that one path for current to flow, all of those objects add up, right? So ohms due to resistance add up directly. Ohms due to inductive reactance add up. Ohms due to capacitive reactance add up. And there's also a relationship between XL and XC. I really like to draw that diagram looking something like this. So I would take both my ohmic values, my resistor, my coil, they would add up. So I would take whatever ohms of my resistance plus the ohms of the resistance of the coil. That would give me my R total. We have our XL and we have our XC. Now this diagram right here is what I would call an impedance diagram. We can only do these in series. We won't do them again in parallel, but in series they're super helpful. Get my R total, get my XL, got my XC. Now the X total, or the net reactance, is the difference between the two. XL and XC are 180 degrees out of phase, so they completely cancel each other out. So I would go, if XL is bigger, XL minus XC, that would put my hypotenuse up here. If XC was bigger, I go XC minus XL, puts my hypotenuse down there. Typically, your hypotenuse would be up here, and that would give you Z total for the entire circuit. Now I'm like, awesome, figure out my total impedance. Then what I like to do is I can figure out my current. I total equals E divided by Z. Pretty common, excellent. That's the relationship with ohms in a series RLC circuit. Now let's talk about voltage again. We know we had those voltage drops, 1, 2, 3, right? One across each load. Let's plot those on a phasor diagram, just quickly, just to talk about those relationships. Because I only have one current flowing through the circuit, often you can use current as a reference on your phasor diagram. My voltage drop for my resistor. Well, voltage and current for a resistor, they are what's called in phase with each other. The current is in phase with the voltage. So my volt drop for my resistor is right there in phase. Now the voltage drop for the coil is the tricky one. So there would have been an angle here, and that angle is going to be important, the theta within my coil triangle. Now, coils have inductance. Inductance opposes a change in current. Therefore, in an inductive load, the current will lag the voltage. If my current is my reference, the current is lagging. That puts my voltage for my coil somewhere up there. It's going to be between 0 and 90. If it was a pure coil, it would be right at 90. But because this one has some resistance, it has some in-phase component, so it kind of builds us a little in-phase, little triangle, which would match this, right? So the angle here for my coil would match the angle inside my coil's impedance triangle. Then we have the volt drop across the capacitor. Now the volt drop across the capacitor is 90 degrees out of phase. Capacitors have capacitance. Capacitance opposes a change in voltage. Therefore, our voltage lags by 90 degrees. So V cap is down there at negative 90 or at 270. So that's what my phasor diagram would look like. Now what I can do is, if I didn't know my total voltage, I could add those up vectorially, right? Applying Kirchhoff's voltage law, which would be that E total equals V1 plus V2 plus V3. Of course, adding them all vectorially. So using an HV chart or using complex numbers, which if you're not familiar, you can check out that video as well. Awesome. So that's ohms, volts, and amps. Now the big thing that I like to focus on when I'm solving these circuits is I love the power diagram. So we know with all of these, right, I've got current flowing through a resistive component. That's going to give me some true power, right? Some heat, some watts. I've got current flowing through a coil. That's going to give me some true power because of the resistive component. It's also going to give me reactive power due to the inductive component, which we call Q. In this case, we'll call it QXL, which of course gives me an apparent power of the coil. Right? Now the interesting thing with the coil is my apparent power angle will match my impedance angle in the coil, right? It's the current flowing through those ohmic values that produce the power. For our capacitor, current flows through a capacitor, we get reactive power, QXC, we'll call it. Now, all of those types of power, right, our active or true power and our reactive or our quadrature power, they can combine. And I like to combine these on a circuit power diagram. So that looks very similar to this. I've got one true power, two true powers, right? Power of my resistor plus power of my coil gives me power total. I have my QXL and I have my QXC. Now, the way those combine, again, it's the difference between the two gives me my net reactive power or my Q total, right? Awesome. So once I have my Q total, right, if it's more QXL, my hypotenuse would be up. If it was more QXC, my hypotenuse would be down. Let's say it was up. Now I got a couple things going on here, and this is great. I can figure out my S total for the entire circuit's apparent power, right? Great. This within here is my circuit angle, or my circuit theta, as well as a quick refresher, that can be my power factor, right? Power factor is the relationship between true power and apparent power, right? P over S. It's always between 0 and 1, right? In this case, because current is lagging, right, it would end up being a lagging power factor. But we got to remember as well, it's always the relationship between the horizontal and the hypotenuse. Therefore, it also equals cosine theta. So those all equal each other. Cos theta equals P over S, or watts over VA, equals our power factor. All right, so a lot of relationships there, super important. And this, again, was just a quick overview of a Series RLC circuit. I do really appreciate you watching, and I do hope that you learned something. So thank you so much. If you like this video, please hit that like button and the subscribe, and check out some of my other videos, and hopefully they can be helpful. Thanks a lot. Have a great day.